Metamaterials were originally defined by Roger M. Walser from the University of Texas in 1999 as macroscopic composites having a man-made, three-dimensional, periodic cellular architecture designed to produce an optimized combination, not available in nature, of two or more responses to specific excitation. Metamaterials are artificial materials structured on a sub-wavelength scale to produce electromagnetic properties beyond those that are found in naturally occurring materials. They are assembled from smaller components made of composite materials such as metal or plastic, and feature a repeating pattern of structures. Metamaterial structures are built at a spatial scale that is smaller than the wavelength it's operating in. Most commonly, metamaterials are used to manipulate waves in the microwave region of the electromagnetic spectrum. Further research is being done to enable metamaterial structures to operate in regions with smaller wavelengths, such as the terahertz band.
Natural materials have their properties determined by their atomic composition. Metamaterial behavior, however, is determined by the structure and properties of the composite materials that it's made up of. By combining different materials in specific arrangements, taking into consideration shape, geometry, size, orientation, and arrangements, metamaterials can obtain unique properties. One such property is the ability to influence both electric and magnetic fields. This greatly expands the range of possible interactions of metamaterials compared to natural materials, which are only able to influence the electric field. Metamaterial structure is composed of unit cells. Each cell is composed of a particular arrangement of materials and therefore exhibits its own specific properties. These properties can be specifically selected for by electronically or mechanically turning these unit cells on or off. It is crucial for these unit cells to be engineered to be significantly smaller than their incident wavelength, usually by a minimum factor of λ/10. Due to the scales difference, incident wavelengths cannot distinguish between unit cells and treat the object as a homogeneous medium. If meta-atoms were larger than or just as large as their incident wavelength, then each unit cell would act as an individual diffracting element, and waves will not be manipulated as desired.
Metamaterials have many unique uses due to their specifically engineered properties. Invariably, the electromagnetic properties of the material are controlled and exploited in order to satisfy a given problem that cannot be solved by traditional natural materials. The many uses of metamaterials include hyperlenses, various types of cloaking, and optical computing. The reason metamaterials are used instead of natural materials because of their ability to interact specifically with the magnetic field as well as the electric field. And the composites made can be controlled to have application-specific properties like negative refractive indices or extremely high permittivities. This allows engineers to control and adapt to the specific circumstances in which the material will function. For example, one of the most interesting applications of metamaterials and the consequence of these unintuitive properties is their use in cloaking technology. By creating surfaces that bend light at an angle that is function of the scattered surface's relative height, an irregular surface can be almost completely concealed from an observer, and will in fact appear as a flat surface. This type of simple cloaking could only work with metamaterials, since the surfaces must be engineered such that they refract at a certain angle based on the scattered object's geometry. This form of cloaking is known as carpet cloaking and is one of the simpler forms of cloaking technologies utilizing metamaterials.
The unique properties that metamaterials exhibit often allow for more effective, inexpensive, and compact solutions to engineering problems. The ability to selectively choose and combine physical properties of different materials is extremely advantageous. As an example, metamaterials can be used to form hyperlenses, which, unlike normal lenses, do not have a diffraction limit and hence can be used to view very small structures like viruses or even DNA. With normal lenses, the resolution is limited to around half the wavelength of the light being captured by the lens. But since metamaterials can have negative refractive indices, this limit is stepped around, and wavelengths below the limit can be captured. Metamaterials can also be used in optical computing, an emerging field motivated mainly by the erosion of Moore's law. Since transistors are getting smaller and smaller and approaching the limits at which quantum tunneling can occur, scientists and engineers must come up with new solutions for computing. One of these solutions is optical computing, which involves the manipulation of photons instead of electrons to transfer and process data. While this field is still quite primitive, it is clear that the unique abilities of metamaterials to manipulate and create electromagnetic phenomena will prove incredibly useful for the future of optical computing. In conclusion, the versatile nature of the field of metamaterials is evident in the multitudes of new and emergent technologies being created and manipulated in various industries and fields of science. The control of the propagation of electromagnetic waves is one of the most useful tools in any industry, and metamaterials are the perfect implementation of this concept.